In this problem, we have a 20-pound link AB that is pinned to a moving frame at point A, and it is held at a vertical position by a string BC right here. This string right here can support a maximum tension of 10-pound force, and we need to determine the maximum acceleration of the frame without breaking the string, which is also the same language as the minimum acceleration of the frame that can break the string. So it's the same thing. And we also need to determine the corresponding components of reaction at the pin A. So first, let's draw the free body diagram when the string breaks, because we're looking to solve for that limiting situation. So when the string breaks, the tension force here is known. That's going to be 10 pounds, because we know that the string breaks when the force is 10 pounds. And then at point A, we have a pin support. Therefore, we have two force components, AX and AY. And also, we have the gravitational center right here, if we assume this is a uniform link. And then we have its weight, 20 pounds here. And that completes its free body diagram. And then we need to draw its kinetic diagram. Kinetic diagram basically is drawing, so let me not draw it on the same one right here. So basically drawing point G, the mass center or gravitational center, with MAG. AG being the linear acceleration. So this is a problem that only involves translation. So with the free body diagram and kinetic diagram, we are ready to write our equations of motion. So our first equation, resultant force along the x direction, equals to AX plus the 10-pound force has horizontal component, which is 3/5, that is given by this 3-4-5 triangle. And that equals to MAG, which is simply MA. The mass is 20 pounds divided by 32.2. That is the gravitational acceleration in the US customary unit system. So 20 over 32.2, that will give you the mass in the unit of slug. And then A, that's our unknown acceleration we need to solve for. Resultant force along the y direction equals to AY minus 20, that's the weight, plus 10 has the vertical component of 4/5. There's no motion along the vertical direction, and that equals to 0. And lastly, let's write a moment equation. There are multiple options. If we write resultant moment about point G, because this is a translation and G is the gravitational center, that will equal to 0. But because if we want to get rid of unknowns, we do not want to have so many unknowns in the same equation, we can also summarize the moment about point A. So if we summarize the moment about point A, that equals to, so the weight force 20 pounds, AX and AY, they all have line of action passing through point A. So point A is right here. Therefore, the only force that has moment about point A is the 10-pound force, the horizontal component, causing counterclockwise rotation. That is 10 times 3/5 with a moment arm of this total length of 7 feet. And that does not equal to 0, obviously, but instead it equals to the kinetic moment about point A, which equals to the moment caused by the kinetic force MAG about point A, which is counterclockwise. It is 20 over 32.28, that is MA right there, times the moment arm. The gravitational center is right here, which has a moment arm of half of 7, which is 3.5. So it's 3.5. From the third equation alone, we can solve for acceleration A. So this equals to 19.3 in the unit of a foot per second squared. So that is the largest acceleration that the frame can have without breaking the string, which is the same as saying the minimum acceleration needed to break the string. And substitute that into here, we can solve for AX to be 6 pounds. And then from here, we can solve for AY directly from this equation to be 12 pounds. So 3 equations of motion, 3 unknowns. We can solve for all of them.